Welcome to the Deep Dive. This is where we take a whole load of information, boil it down, and give you the insights that really matter. And today, we're doing something a bit special, kicking off our CSWIP 3.1 exam prep series. Now, for anyone not in the know, CSWIP, that's the certification scheme for welding inspection personnel. Pretty much the gold standard. Our mission today, simple. We're tackling some key multiple choice questions, stuff you absolutely need to know if you're prepping for that CSWIP 3.1 exam. Think of it as sharpening your skills.
Exactly. And look, it's not just about handing you the answers. That wouldn't really help in the long run, would it? We want you to really get why an answer is correct. Understand the thinking behind it. That's what helps you on the exam, sure. But also out there, doing the job. It's about building that solid understanding, so the knowledge actually sticks.
I like that. Yeah, it's about genuine understanding, not just memorizing facts. We'll walk through how an inspector thinks, right? From spotting something to figuring out what it means, all through these exam-style questions. So let's jump in. First up, something really foundational, getting to grips with defects. Okay, let's unpack this first one. This deals with how serious different welding defects are compared to each other. Really important for prioritizing on site. The question is, lack of inter-run fusion would be considered more serious than. And here are the options. A, slag inclusions would be considered more serious than answer A, B. Lack of fusion, surface breaking, would be considered more serious than answer A, C. Both answer A and C would be considered to have the same seriousness as they are both lack of fusion defects. What are we thinking here?
Right. The correct answer here is B. Lack of fusion, specifically surface breaking lack of fusion, is considered more serious than lack of inter-run fusion. And the reason, it's pretty fundamental. Think about where the defect is. A surface breaking one, it's right there, open to the world, open to stress. It's like a little crack already started on the surface. Makes it much, much easier for a bigger crack to grow from there, especially under load. It's an immediate risk point. Now, compare that to lack of inter-run fusion. That's internal, right? Buried within the weld metal. Still not good, obviously you don't want it. But it's somewhat shielded. It might take more for a crack to really get going from an internal defect compared to one right on the surface. And slag inclusions, they're usually more like little blobs, volumetric. They weaken the weld, sure, but they're generally blunt, less likely to kick off a sharp crack compared to that planar, sharp nature of lack of fusion.
That makes sense. It's about the shape, yes, but also very much about the location surface versus internal. So an inspector's eye is immediately drawn to those sharp surface breaking issues. But let me throw a curveball here. What about those really high-spec jobs, aerospace, nuclear, where internal flaws are also a huge deal? Could you get a situation where, say, a lot of internal slag, even though it's blunt, might actually be just as worrying as a small surface crack? How do you balance that in practice?
That's a really good question. And you're right, it's not always black and white. The general rule holds planar surface breaking is usually top priority, but context is absolutely key. In those critical applications you mentioned, a dense cluster of porosity or maybe large aligned slag inclusions deep inside. Yeah, that can become a major concern. It might create a significant weak zone, especially under fatigue conditions where things are getting stressed repeatedly. So while the type of defect is important, you also have to consider the density, the location relative to stress, and the overall demands on that specific component. It becomes a more complex risk assessment.
Right, so it's a starting point, that hierarchy, but you've always got to apply it to the specific situation. Okay, understanding the impact is one thing. What about the cause? Let's look at burn through. A real headache sometimes. The question asks, burn through. And the options: A, may be caused by the root gap being too small. B, may be caused by the travel speed being too fast. C, may be caused by the welding current being too high. D, all of the above.
Okay, for this one, the answer is C. Burn through is maybe caused by the welding current being too high.
Ooh.
It's pretty direct, really. You crank up the current, you crank up the heat input, too much heat, and that weld pool just gets too big, too fluid. Gravity takes over and boom, it falls right through the base metal, especially on thinner materials or right at the root where there's less metal to soak up that heat. Now, the other options: a root gap that's too small. That usually causes the opposite problem, lack of penetration. Travel speed too fast. That tends to give you a ropey bead, maybe undercut or lack of fusion because you're not depositing enough metal. So while parameters interact, excessive current is the most direct cause of just melting right through. Although I should add, traveling too slow at a given current can also cause it because you're putting too much heat in one spot for too long.
Ah, okay. So it's fundamentally about too much heat energy in one place, and high current is the main way that happens. But it's like walking a tightrope, isn't it? Too low current, you don't fuse properly. Too high, you blast through. You mentioned thin materials are prone. Are there other things that make burn through more likely, even if the current isn't ridiculously high, like joint prep or something? And how does that travel speed fit in again, even if it's not the primary cause?
Yeah, definitely other factors. Base metal thickness is huge, like we said. Thinner stuff just can't handle as much heat. Joint design matters too. An extremely tight root might trap heat, while a massive gap might make it hard to bridge initially, but perhaps less prone to sudden burn-through once established. Preheat or lack of it changes things too. And travel speed. Well, if your current is maybe borderline high, slowing down too much lets that heat build up excessively. So while high current is the direct trigger, slow travel speed can definitely contribute by not moving that heat source along quickly enough. It's all interconnected, you see. Getting that balance of current, voltage, travel speed, and considering the joint and material, that's the art of welding, and what an inspector needs to understand when troubleshooting.
Right, it's that whole combination, the interplay between everything. Okay, super important. Let's switch gears slightly now to a calculation, something every inspector needs to have down pat. This is about the strength element. The question: the throat thickness of a 19 millimeter fillet weld is, and your options are A, 27.5 millimeters, B, 24 millimeters, C, 13.3 millimeters, D, 12.5 millimeter.
Okay, the answer here is C, 13.3 millimeters. And this comes from a standard calculation for an ideal equal leg fillet weld. We take the leg length, which is 19 millimeters in this case, and you multiply it by 0.707. That 0.707, it's not just a random number, it comes from the geometry, basically trigonometry. For a 45-degree fillet, the shortest distance from the root to the face, that's the throat, is sine or cosine of 45 degrees times the leg length. And c to cosine of 45 is about 0.707, so 19 millimeter times 0.707, that gives you 13.433 millimeters. Looking at the options, 13.3 millimeter is the closest. And knowing this is crucial because that throat thickness, that's what determines the weld's strength effectively. It's the critical dimension for carrying load and shear. Get it wrong, and the strength calculation is off.
Right, 0.707 times the leg length. Got it. And that really highlights why it's so important. It's not just a number on a page. It's directly tied to whether that weld can do its job safely. What are some common mistakes people make here? Is it just miscalculating, or maybe measuring the leg lengths wrong, or perhaps not accounting for the actual weld shape? It seems that a small error could have big consequences.
You're spot on. Consequences can be huge. A common mistake is simply confusing leg length and throat thickness. They aren't the same. Another is assuming the weld is perfectly flat or miter. Wheel welds often have some convexity bulging out or concavity dishing in. Convexity can sometimes add to the actual throat, making it slightly stronger than calculated, but excessive convexity is often a defect itself. Concavity, though, directly reduces the throat thickness below the theoretical value, making the weld weaker than designed. So the inspector isn't just calculating the theoretical value, they're comparing it to the actual weld profile using gauges, making sure that minimum required throat thickness is actually present. An undersized throat is a direct reduction in safety factor. That's why precision matters so much here.
Undersized throat means an undersized safety factor. Powerful way to put it. Okay, so we've looked at seriousness, causes, measurements. Let's talk about classifying defects again, but from a slightly different angle. This question is about the nature of defects, non-planar defects, and the options are A, are always repaired. B, their existence will result in the removal of the entire weld. C, they're not usually as significant as planar defects. D, they can only be detected using radiography.
All right, the correct statement here is C. They are not usually as significant as planar defects. This goes back to what we touched on earlier. Planar defects, think cracks, lack of fusion. They're like sharp knives within the material. Flat, two-dimensional, sharp tips. They concentrate stress incredibly effectively and are prime initiators for fracture. Non-planar defects, on the other hand, are volumetric, three-dimensional. Think porosity, little bubbles, or most slag inclusions. They're generally more rounded, blunter. Because they're blunt, they don't concentrate stress nearly as severely as planar defects. So while they are imperfections and might need addressing depending on the code or standard you're working to, they generally pose less of an immediate threat to structural integrity compared to a crack of similar size. The other options just aren't true. Non-planar defects aren't always repaired. Acceptance criteria often allow for a certain amount. They certainly don't always mean removing the whole weld, and radiography isn't the only way to find them. UT can find some, and sometimes large ones might even be visible after sectioning.
It's fascinating how much the shape tells you about the danger level. That distinction between sharp planar and blunt volumetric is key. But you said usually less significant. We talked about clusters earlier. Are there other times when a non-planar defect does become a really big deal, maybe depending on the material or the type of loading? Can porosity, for example, ever be truly critical?
Absolutely. The usually is important. Context again. For instance, in materials very sensitive to hydrogen embrittlement, porosity might be more critical if it indicates high hydrogen levels. Or think about fatigue again. Even blunt defects, if they're numerous or located right at the surface or in a high-stress region, can act as initiation points for fatigue cracks over many cycles. Also, some codes have stricter limits for non-planar defects in certain applications, like pressure vessels, where leakage through interconnected porosity could be a major issue, even if it doesn't cause immediate fracture. So yes, while the general rule is useful, a good inspector knows the exceptions and considers the whole picture: material, service, stress, location.
Excellent point. Never just blindly apply the rule. Okay, final question for this session. Let's nail down some terminology. Getting the language right is important, especially when you're talking about efficiency and process control. The question: in an arc welding process, which of the following is the correct term used for the amount of weld metal deposited per minute? Options: A, filling rate; B, deposition rate; C, weld deposition; D, weld duty cycle.
The precise term here is B, deposition rate.
Right.
That's the standard industry term for the weight or mass of weld metal laid down in a specific unit of time. Often kilograms per hour, maybe pounds per minute, depends on the context. It's a fundamental measure of productivity. How fast are you actually putting down weld metal? It's critical for estimating job costs, consumables, labor time, and for comparing the efficiency of different welding processes or procedures. It's different from, say, duty cycle, which is about the machine's capability, how long it can run at a certain output before needing to cool down. Deposition rate is purely about the output of metal. Filling rate and weld deposition are just less precise ways of saying the same thing. Deposition rate is the one.
Deposition rate. Got it. So it's the direct measure of how much metal hits the joint per unit time. How does this actually play out on a job site? Why does an inspector, not just the welding engineer or the accountant, need to care about deposition rate?
Well, several reasons. Firstly, welding procedures, WPSs, often specify parameters that result in a certain deposition rate range. If the actual rate seems way off, it might indicate the welder isn't following the procedure correctly. Wrong parameters, maybe poor technique. That could affect weld quality. Secondly, during procedure qualification, PQR, deposition rate is often recorded. It helps characterize the process. And sometimes very high deposition rates, while efficient, might bring other challenges like controlling the heat input or ensuring adequate fusion, which an inspector needs to be aware of. So it connects efficiency to potential quality issues. Understanding it helps the inspector assess if the job is being done not just correctly, but also effectively and within the qualified parameters. It links the economics back to the technical execution.
That links it all together nicely. Efficiency and quality aren't separate things here. Okay, wow, we've covered quite a bit of ground. We looked at why surface breaking lack of fusion is generally nastier than internal lack of fusion. We pinned down high current as the prime suspect for burn through. We ran the numbers on fillet weld throat thickness, that crucial 0.707 factor. We contrasted planar versus non-planar defects, understanding why shape matters so much. And we clarified deposition rate as the key term for weld output. Really dug into the why on these.
Exactly. And hopefully you see how these pieces fit together. It's not just about passing the CSWIP exam, though obviously that's important. It's about building that core knowledge, that critical thinking you need to be a competent inspector. Knowing this stuff helps you make informed decisions out there, ensuring things are built safely, reliably, and efficiently. It's about preventing problems, not just finding them.
Couldn't have said it better myself. And to leave you with something to chew on, we've talked a lot about established defects and parameters today, but think about the future. How might things like, say, additive manufacturing, 3D printing with metal change? How we even define a weld or assess defects? Or how could AI-driven analysis of NDT results potentially shift an inspector's focus from finding flaws to predicting performance based on subtle material characteristics we don't even routinely measure today? What's the next frontier beyond the current rulebook? Lots to think about. Keep digging deeper, keep asking questions. That curiosity is what makes a great inspector. Thanks for joining us on this deep dive, and we'll catch you next time.